This video is my physics lab for testing out the pressure of a water gun, and this will be basically the pressure you receive from the water when the gun shoots some water to you. Okay, let's start with the lab. Okay. First you gotta understand KE, or the difference in KE equals the negative difference in PE. This is the conservation of energy. And to represent this in terms of water and fluids, you just have to transfer Ke into half rho v squared equals, actually not mgh. I wrote this one wrong. Rather, it's just rho gh, because rho is the form of mass for liquids, because it represents the density per unit. I think it's meter uh meter cubed, I think. Yeah. And then so this diagram is my water gun, and the H basically represents the height of the water that it will travel. This is because the conservation of energy tells me I can derive the I can derive the potential energy from the kinetic energy, because if I shoot it straight up, it will be the same route back and forth, which we also know rho gh is the pressure. So, but there's a second method. That was the first method. The second method, I think, is using Bernoulli's equation. And in Bernoulli's equation, in this video, I was just finding where the formula sheet was. However, the basic idea is that I'm using the already known terms of the water gun, and then try to find a way of the relationship between how much time it took for my water gun to empty the water in it. But yeah, let's start step by step. First, Bernoulli's equation. Mess it up here, but yeah, okay. Bernoulli's equation is P1 plus rho gy1 plus half rho v1 squared. I think I forgot to write the sub y, but yeah, you get the idea. And then plus P2 rho gy2 plus half rho v2 squared. Okay. And okay, basically I'm gonna explain it right here. What I'm gonna do is delete basically everything except P1 on the left. The reason is that you don't know, you actually want to represent the pressure of your water gun in the initial place, in an initial condition, or in the beginning, and then you want to represent it as a cause, and then the effect is the kinetic energy that came out. So the pressure caused the kinetic energy. And I would like to think it like this. The PE equals 0 because it's not moving. So it has to be 0. Rather, the P is actually the source of the energy that's, or not even energy, the source of this, velocity of water that goes out of the water gun. So I said pressure is the product of the potential energy. So yeah, you get the idea. The pressure exists. The pressure exists while the kinetic energy doesn't exist. So that's how I think it. That's how I think it is. However, I don't think I should be explaining this, because later, my experiment actually fails, and this is not an ideal procedure. However, I'm just explaining to you this method too, to give you a broader perspective of how this experiment could be conducted. However, yeah, okay, back to my thing. I wanted to calculate, I want to find a relationship between the flow rate and Bernoulli's equation, right? because flow rate gives you the velocity. So in order to get pressure, I need to find the velocity. So I need to set up a relationship between them. So the flow rate, first of all, equals volume over time. Basically, the flow rate is how much water flew, through your thing in that certain time. This gives you the kind of the speed of your water, I guess. But yeah, water does not come in like 2D. It's not meter squared. It's meter cubed. So yeah, I basically thought I could divide the flow rate by area. It will give me the velocity, um, which if I were to do that, I need to divide the volume by area, and then divided by t, the time it traveled. Okay, however, um, what area? Like, what area should I divide? Is it the area of the water gun, like the cross section area of the water gun, or should I think about something else? Okay, I needed to think of something else because the volume of water comes out at this little hole on top of the water gun, right? The nozzle. It comes out of the nozzle. However, the volume is, it's very big. It's a very big volume, but it's a very small nozzle. So I needed two area. I needed another area. Hence, V equals volume over the area of the nozzle, and then the whole thing divided by time, the time it takes to empty the water. Now, why do I say this won't work? First, I don't know how much how much water my water gun needs. Or like, I don't know how much I should add to measure. Because if you add too much, you cannot empty it in one shot. If you add too less, you can't really gather the water because of the structure of the water gun. So you cannot suck up the water when the volume is too small. Yeah, that's why I thought this experiment wouldn't work out. But yeah, I've drawn a diagram. This is how it should have looked like. You see, if it is filled with water, basically I just need to measure the time that it took for this to empty, for this water gun to empty the water that it used to have. Yeah. So as you can see, that is just a enlarged diagram of my nozzle. I would say that's R2 because I needed another area. And oh yeah, by the way, the volume equals pi r squared times h. And I'm basically just measuring h is the total distance of total water that has traveled. Like total water is the volume time, it's just the volume. So the total distance of the total volume that has traveled is basically h. If you understand, you can imagine like it's moving. But yeah, as you can see, it didn't work out. I just didn't know how much water to add. But yeah, you can see me just working on method 1 over here. So I thought of just measuring how high the water will travel. It's kind of funny, but I got on the ground and then I tried so hard to mark it up. However, I found out that this method won't work because the pressure is so high. The water travels so fast or so high. It just goes to the roof. It goes all the way to the roof of the ceiling. Sorry, it goes all the way to the ceiling. It wasn't a good way, so I found another way. I thought about it. Using my physics brain. I have a higher ceiling, so I can test something else. Test it out in a different setting. Okay, so right here, I just measured it. I tried to do it from the ground. However, this led to another problem, which I cannot see anything. There's not enough light, and my light bulb is broken in the hallway right there. This actually led to a smarter solution. Okay, my sound is on for this one because I really wanted you to hear that I'm actually spraying water. However, what I did was basically I just tried to find a sweet spot that the water could get straight to the ceiling, so that I know it's gonna get to the ceiling, but I just need to measure the distance that it has traveled. I have a fixed point, which is the ceiling, and I just have to adjust a little, and then adjust it to the sweet spot on the bottom, which you can see. I have a lot of problem measuring, but I got like 8 foot 9 inches and 8 foot 10 inches as my mark, as you can see from my video. So if you transform or mm, if you convert 8 foot 10 inches, or actually I found like the middle of these two values, which is 8 foot 9.5 inches. Now, if you convert this into meters, since all of our equations are based in meters, um, it gets you 2.93 meters. However, fun fact, when we calculate the pressure, the unit is PA, and usually we represent it in kilo PA. However, in America, we also use PSI. That is just something for per inch, right? PSI square inch, something square inch. I think pressure square inch, something like that. But yeah, if you wanna convert P PA to PSI, you just have to multiply it by 14, which right here I just have to plug it in. The units is a bit confusing, so I just marked down the units. First of all, P equals rho GH, and the rho, which is the density of water, is 1,000 kilograms per meter cubed, and then you times it by G, which is the gravity, which is the acceleration, which is 9.81 meters over a second squared. And then you just bring in my height. My height was I measured, which I already converted, was a 2.93 meters. And then you can get rid of two m's. You can get rid of like the 3 minus 2 on the exponent on the denominator, and then you get meters per second squared. No, kilograms per meters times second squared. And yeah, by the way, you just want to multiply like those numbers together, and then I guess I've gotten a pretty reasonable number at the end, which was like a 28.74. Yeah, this step was just me putting it in the calculator. However, yeah, it was a 28, like 2,000, 28,000 something. However, if you want to convert it to like kPa, would be it would be 28.743, which if I use what is it called, if there is only, I literally forgot this word, if there is only two significant figures, it would be a 28.74 kPa, which in terms of PSI, it is a 300 something. It's 302, I think, 302. So I think this makes sense. It won't kill anyone, but yeah, it was pretty fun to discover how much the pressure was that a water gun could produce or yield. And yeah, that water went really high. It went all the way to the ceiling. I had to switch a place. It was a really fun experience overall. And yeah, I really enjoyed it. I just did it now. And it's a good way to culminate my year. So, I hope you enjoyed this video. I'm just gonna finish the sentence on the screen right now. And yeah, I'll jot down some notes on my lab notebook. Actually, I need to write it out. I need to write everything on my lab notebook. I'm gonna have fun with that. I've been really quiet in this video because everyone is asleep. But yeah, I hope y'all enjoyed watching this video, And credits to Father Luca for supporting my videos too. And yeah, it's really fun. It's a really good year, and I'll see you.